Hello. So, my name is not Kiko Fernandez Reyes. He had a last-minute emergency and had to go back to Sweden. So he asked me to give the talk instead. So my name is Elias. I'm not at Uppsala University. I'm at KTH. So you should change that as well. But this is actually work that I did while I was at Uppsala University. And I did this work with Kiko and a bunch of other people. This is an experience report that comes out of something called the Upscale Project. The Upscale Project was a collaboration between Uppsala University, Imperial College in London, CWI in Amsterdam, and the University of Oslo. And among other things, it included the development of a language called OnCore. Now, OnCore was, or is, I should say, an object-oriented language. It has classes. It uses actors or active objects for concurrency. It has all the bells and whistles that you'd expect from an object-oriented programming, subtyping via traits, parametric polymorphism, and so on and so on. Close to my heart is capability-based type systems for concurrency control that ensures that there are no data races when active objects are sharing passive objects. So if you'd like to know more about OnCore, especially about the capability-based type systems for concurrency control, there is a PhD thesis, an excellent PhD thesis, called Capability-Based Type Systems for Concurrency Control that you could read instead. But I'm not here to talk about OnCore today. Rather, I'd like to talk about the OnCore compiler. Because the OnCore compiler is about 15,000 lines of Haskell, and it's translating OnCore down to C, and then we use Clang to compile C. And about roughly half of it, 7,000 lines or so, is the type checker of the language. So who is this experience report for? Like, it has Monadic in the title, so obviously it's for the enlightened few who can understand these things. And the answer is no. The answer is that if you are one of these people who can write Haskell with one hand tied behind your back, you will most likely not learn anything from this experience report, actually. No, this report is for this guy. This is me in 2012, right before we had even started thinking about OnCore or anything. I didn't know, well, I had brief experience with Haskell. Most of us in the group had played around with Haskell, but it was not a deep experience. So the reason we wrote this experience report was that recently we got to talking about how the current design of the type checker is sort of kind of nice. We like it. And it sort of grew into its current shape over the years. And we hadn't really seen this design described anywhere. So really, this report is sort of like the tutorial that we would have liked to read back in 2013 when we started this work. So there are few or no novel results, but sort of we'd like to think that we've put them together in a case study that's sort of close to our hearts and hopefully close to some of your hearts as well, that is implementing an object-oriented type checker for an object-oriented language. So in short, this is an experience report on how to use a global environment, add backtraces, throw multiple errors, where usually when you're doing exceptional stuff in Haskell, you only throw a single error, or if you want to report multiple errors. Provide warnings is a similar thing. Maybe I think the deepest we go is to make sure that, well, to use Haskell's type system to track which compiler phase you are currently in. So this prevents the sort of bugs where, for example, during code generation, you need all the AST nodes to be annotated with their types. And maybe you forgot to do that in the type checker, and so you would have a crash with a terrible error message. So this way you can ensure that this doesn't happen. And in addition to these things, we briefly discussed how to add some of the object-oriented features that is not in the language that we start from. Yeah, so the sort of techniques used in this report it's type classes and GADTs, semigroups, monoids, functors, blah, 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 scary words. But remember this guy, he didn't know any of this stuff when we started. So hopefully this guy would have been able to read this report and follow along and learn while doing it, instead of finding the single paper on how to use GDTs or the single paper on how to use model transformers or whatever. And yes, I did edit Kiko's slides mostly by inserting pictures of my own face. So we do assume a basic level of Haskell knowledge, of course, otherwise it wouldn't really be feasible. But not a lot more than you would get from a bachelor level course on functional programming. So to make the presentation feasible in the paper, we start from a subset of OnCore. This is supposed to represent your favorite object-oriented language. It has classes, which has fields and methods. Fields have qualifiers to denote if they're reassignable or not. This could be public or private as well. This is just to capture some kind of qualifier. Expressions use let bindings to keep scoping simple. Actually, in the OnCore compiler, there's variable declarations. There's an earlier pass that transforms regular imperative variable declarations to this kind of form. Method calls, field lookups, constructor calls, typecasts, anonymous functions. So basically, there should be no surprises here. Now, again, I want to reiterate that the main focus of the paper is not the features of the language itself, but the features of the type checker. Like, what does when you run the compiler, what features does the type checker have? The initial approach looks something like this for type checking. We use type classes to achieve ad hoc polymorphism. So for each kind of AST node A, there's a function type check that, given some environment, takes an A and either produces a type checking error or returns the same A but annotated with types, assuming that the program is type correct. So nothing strange. So for example, there's a data type for expressions, of course. Each expression carries with it its type. So this starts out as nothing, and then when it's type checked, it's annotated with the type, so it carries with it. And then the instance of type checkable for the expression data type shows lists all the different cases for type checking. Note here the use of throw error, which is from the exception library in Haskell. So that's how we report that something is wrong. So this initial version is about 450 lines of code with both the data types, the data type declarations of the entire abstract syntax tree, and the type checker. But there's no parsing in this in the artifact. There is no code generation. We're focusing only on the type checking part. So let's have a look at just a simple example of the kind of things that we do, namely adding backtraces. So what do I mean by a backtrace? Well, a backtrace is something that's mainly used for providing nicer error messages, but it can be used for other things as well. So let's say you have this program that has a bug. Spot the bug. I'll give you 4 seconds. I'm a bit over time, so I won't give you 4 seconds. So there's no field Y in class C. This is the simplest error message that we can produce. Arguably, a nicer error message would be to say, there's no field Y in class C, and I found this out while trying to type check this.y in method foo in class C. That's something that could be nice to have, right? So the general idea here is that we define the backtrace as being a list of backtrace nodes, and each backtrace node contains something that can be type checked. For example, there's a backtrace node for classes containing a class definition. There's one for methods containing a method definition, and so on. And really, if we think about it, we have these functions that we go through when we type check a program. And when we're type checking a class definition, really what we want to do is to push one of these backtrace nodes onto that to remember which class we're in, when we're type checking a method, we want to push that. Every time we're type checking an expression, we want to push that so that we can build a backtrace, and then simply build the error message by just popping this thing one by one. So what we do is we take this backtrace that we've defined, we put it in the environment so that it's always available to us. And instead of using throw error, we just use a little helper function called tc error for type checking error that throws the error but attaches the backtrace of the environment onto the error so that when you're reporting this thing, it's available. So this seems like it would be a tedious thing, because we have all of these functions and we have all of these cases, and every time we do a recursive call, we have to insert this thing that pushes stuff into the backtrace. But it doesn't have to be like that. So we were in a situation that looked like this, and when adding backtraces, we moved to a situation that looks like this. So now there's a function called doTypeCheck that is exactly the same function as typecheck used to be. And then there's a function called typecheck, which has a default implementation that just calls doTypeCheck and pushes the thing that we're type checking onto the backtrace. Okay, so what kind of, how do we get this to work? Well, the only things we have to do is to change the left-hand sides of all of the implementations from doTypeCheck to typecheck. And then we have to find and replace all of instances of throw error with tc error to make sure that we're actually pushing stuff. We're attaching a backtrace to the error. So that's it. Like we have some implementation. We want to extend it with this feature, and we don't really have to change the implementation that we have in any major way. Like all of this could be done almost automatically. So inside here, we're still calling the type check function, the one that actually remembers the thing, the backtrace. So sort of like this is the story for all of these extensions, that they can be done without any major changes to the existing code. So these could be done in any order and without sort of interacting too much with each other. There are other things in the paper. So the global environment, that's just reader monads and some monad transformers, throw multiple errors, some other type classes, some more monads. The deepest we go is this tracking faces thing where we use phantom types to encode some sort of type state. And then there is some comparison to other languages and their type checking implementations as well. I'd like to show a demo, but I don't have time, but I can at least point you to the artifact. So that there is an artifact here that was evaluated and accepted, and it sort of follows the paper closely and on a per section basis shows how to add these things. And we're very happy that the reviewers were happy with this thing. Apparently it takes the reader by the hand and guides them through the code, which is sort of exactly what we were hoping for. So we were really happy with this thing. So to summarize, this experience report acts as a tutorial for researchers who want to use a functional programming language like Haskell to implement a type checker, even though the language that they're implementing might not be functional in itself. And it's for people who might not already have a lot of Haskell experience. So it covers basic things like simple monads and type classes, but also goes slightly deeper into other language features. But importantly, it's being done in a case, with a case study that's sort of close to a language implementer's heart. And it should be familiar to people here at SLE. And if you want to check it out, there's an artifact that we've tried to make as accessible as possible. There's also from the SLE webpage from the proceedings, you should be able to find a version there as well. So I'll take some questions if you have them. Thank you. So the question was, if I could time travel, what would I have done differently? As if doing the project again, if I could time travel, I have grander plans than that for my time traveling machine. What would I have done differently? I don't know. I mean, it's a social thing as well. Like, we had tons of fun learning about this stuff. I think, like, I can think of detailed things. I would have been more aggressive with information hiding than I was before. Like, now I know which sources to use to, like, can I bring a copy of this report to myself? I don't know. Yeah. No, but I think we were lucky in our exploration of the design space, because we came to this design of the type checker, and it worked out nicely sort of from the beginning. Like, we were always expecting to sort of tear this out and do it again once we had learned more stuff, but it worked out even nicer. The code generation code, on the other hand, that's terrible and should never have been. That also tries to do type system magic to make sure that you're building a syntactically correct C AST, but in practice it just means that you have to convince the type checker that yes, this is actually an L-val. I am allowed to assign to it. So I probably would have made that simpler. But in terms of the type checking code, I'm actually pretty happy with how it turned out. Jorel.
So another use, thank you for Michael. So
Thank you.
another use of your system might be for comparing, benchmarking other approaches to type checking. So is your system, does it have enough, it has a nice automatic test suite for checking the type checking, so that others could use the same language and test cases to do type checking in another way in order to understand how different approaches work?
So the question was if this thing could be used, like our artifact, I guess, could be used as a basis for benchmarking other approaches. I think it's very difficult to quantitatively measure the quality of a type checker. Like, you would have to do like a quantitative study. Is this nice code? Is this a small change? What does a small change mean? Like, there is a test suite. I wouldn't go as far as saying that it's nice, but it's there at least. There is an attempt at doing it. I mean, I would love to see pull requests to this repo with other approaches, other ways of doing this thing. There were suggestions by the reviewers. If you're in the room, thank you very much. We didn't have time to implement them yet, but there were suggestions for how we could do things differently, and it would be interesting to have those there, if nothing else, as a library of compiler implementation techniques.
Yeah, that's what I also was thinking, because even if you make a decision like the decisions that you have made, you can also discuss what are the alternatives and why are you choosing this particular monad or this particular approach, and what were possible choices, because not everybody for whom this is possibly useful will be building a type checker exactly for a language like this.
No, that's very true. And I think that this experience report is really one point in the design space, and it allows you to. So I'm implementing my new type checker. I was thinking about using Haskell. I've heard good stuff about monads. I can look at this. What did this give them? Like, what worked, what didn't work for this design? So I guess that's what we're trying to do, rather than really imposing, like forcing someone to do it. Like, if I had the time, I would like to try to do it in a different way, but I would have to find a project where this would make sense.
Any other questions? Can you automate this artifact and make it a type checker generator?
Type checker generator. Well, I guess I mean you should be talking to Henrik here. That's what you're doing, isn't it? Like, going from something declarative to an actual type checker that you can run and use.
Are you sure these tools can generate 7,000 lines of estimate?
I don't know. Can it?
There would be less than 7,000 lines, I think.
So less than 7,000 lines.
I don't know if I could actually do it in this.
Right.
Oh, 6,000 would have to. Any more